All right, so today's notes is about the derivative. It's an intro to the derivative. We're going to start with just like kind of refreshing on what we already know. So, secants and tangents, we're going to review that very quickly. Here's a picture of a secant line. If you don't have a picture of a secant line in your notes, please put this picture in there. And then we're going to add to this picture, we're going to add f of a, which is a y value at a. So that's f of a. And then we're also going to add the value f of b, which is like the y value at b, so f of b. Please make sure, again, that you have a picture of a secant line in your notes. And then I want you to answer this question. What is the slope of the secant line? What do we call the slope of the secant line? This is what we wrote notes on yesterday. What is the slope of the secant line? All right, slope of the secant line in calculus, the slope of the secant line is the average rate of change. Average rate of change. And then let's make sure we have the equation for that. So we represent that as an equation, AROC from A to B equals f of b minus f of a over b minus a. That is the slope of the secant line, average rate of change. All right, next, let's talk about the slope of the tangent line. So let's make sure we have a picture of a tangent line in our notes. And I don't have the tangent line drawn because I wanted you to see me draw it. Tangent lines bump up against the outside of a curve at a certain x value. So here's x equals a. And the tangent line is going to bump up against this curve at this point on the outside. So it would look something like this, and it represents the slope at that point. It should kind of like match the slope at that specific point. So that is the slope of a tangent line. And then how do we find the slope of a tangent line? We should know that from yesterday. So I want you to describe that process, please. In the box, please explain how would you find the slope of the tangent line? What did we learn last class? Okay, so to find the slope of the tangent line, we use AROC at x equals a and x equals a 0.00001. It's a point super close to a. So like it would be a and then a 0.00001. That works because it's basically doing average rate of change secant at 2 points that are super close together. And so they kind of make the tangent line. All right, now let's review. Please write this down if you don't already have it, and then we're going to go more in depth. The derivative of a function, f of x, at the point x equals a, is the slope of the line tangent to the function at x equals a. And then you need to make sure that you have this entire thing. So if you need to, pause the video. And we're going to talk about how to write and say the derivative. So under this definition, I want you to write what I have under the definition. And then we'll talk about like how to say this. So this thing, make sure you have this. All right, so the formula is said f prime of a. That's how you say this thing, f prime of a. And the way you write it is, like I'll write it right here in case you want to see me write it, f prime, parentheses always stands for of a, f prime of a. And this also means, so you need to write this down, this also means the derivative of f of x at x equals a. That's what f prime of a is. And again, the derivative is the slope of the line tangent to the function at that x value. Okay, so now let's really quick go over alternate definitions of the derivative. So, we have two definitions. I lied. I'm going to come back up here. So in your notes, please write f prime of a equals, and we're actually going to write an equation for f prime of a. So f prime of a equals, and this is one definition of the derivative using limits. So we're going to do two different definitions, both using limits. The first one is the limit as h approaches 0, this one's the most common definition used in calculus, of f of a plus h minus f of x, or sorry, f of a over h. Cool. And let's go ahead and get the alternate definition down. That's the alternate definition using limits. And I'm going to do that one in green. So the alternate definition is f prime of a equals, I'm going to write it right here, sorry. F prime of a equals the limit as x approaches a of f of x minus f of a over x minus a. And let's really quickly talk about what these two definitions mean, and then we'll actually do some problems with them. So I'm going to draw a graphical example of each one of these, and I think it'd be very helpful for you to draw those in your notebooks as well. So we're going to do the same function. So let's draw two graphs, the same function, and we'll talk about what each of these limits is doing. So we're going to have the x value a on both of these graphs, x value a, and then we'll have the y value, f of a, on both of them. That'll be like our bottom y value, f of a. Okay, and then let's just draw the same curve. So I'm going to draw the curve in pink. We're going to have something like this. Cool. Those are supposed to be the same. Pretend they're the same. All right, and then we have the point a comma f of a. That's right here. Then we have, let's add two things to our graph. So for this graph, the top one, we're going to add a plus h as an x value. So we're adding something to a, so it's going to be to the right, a plus h. And then for the next definition of the limit, we're going to add we're just going to add the x value x to the right. So x would be to the right. And then we need to add those y values, corresponding y values. So put a point here, and that y value would be f of a plus h. Same with the x, put the y value on there. We have f of, plug in x, whatever x is. Okay, so we have f of a, f of x on our bottom graph, f of a plus h on our top graph. Okay, so now let's look at what these two limits are doing. So let's only look at the top one. The top limit, this is saying, this numerator right here is saying a plus f of a plus h, the y value a plus h minus f of a. So that means the distance between here, this distance. And then h is getting closer to 0 because our limit is saying h is approaching 0. So what that really means is this distance is getting smaller. This a plus h is getting closer to 0, so it's kind of like we're moving this closer and closer to f of a. We're making that distance smaller. And then on the bottom, because h is getting closer to 0, so right here h is getting closer to 0, that a plus h is going to move closer and closer to a this way, to the left. All right, so if we were to draw the secant line is the line connecting between the two dots. It looks like this, right? But as h gets closer and closer to 0, because we're taking a limit, remember, as h gets closer to 0, as that happens, this dot right here is going to move down the line, down the curve, closer and closer and closer to the actual y value at x equals a. So we're taking an orange secant line and we're turning it into a derivative line. We're turning it into a tangent line. Like it's going to get so close that it looks like a tangent. It looks like a tangent at that point. Does that make sense? If it doesn't, don't stress. It's not going to be horrible if you don't get this. I'm just trying to explain like what we're doing with these limits. Okay, so for the second limit, for this one in green, we have f of x minus f of a, but x is getting closer and closer to a. So this x value is getting closer and closer to a, similar thing. And that would mean that f of x is also going to get closer and closer to f of a. So again, we have this dot that's right here, like the purple one, moving that way down the line. So we're going to go down and down and down the curve until we get so close to a f of a, to this point, that our orange secant line, our original orange secant line, because y'all, this like piece inside the limit, it looks like a rock, right? But we're taking the limit of a rock, so that's why I'm drawing like a secant line. These are both average rates of change. They're slopes. That orange secant line is going to turn into something very, very, very close to a tangent line, and we'll eventually be finding the tangent or the derivative. That's why it's called the limit definition of derivative. We're finding the slope of the tangent line at x equals a. We're finding the derivative at x equals a by taking these limits. So you need to know both of these definitions of the derivative, both of these limit definitions of the derivative. And now let's see how to use them, or how to find the derivative now. Cool. So we just talked about why those two different definitions are the same. Now let's really quickly go over different derivative notations. So these are all the same thing. These all mean the derivative. We have three different things. We have dy dx. I'm going to write out what they mean. We have, and how to say them, y prime. And we have dy dx of f of x. So let's go ahead and just like write all of those down and then write what they mean. Dy dx, derivative of x. This is how we say this. We can say dy dx, but it means the derivative of x, of y with respect to x. With respect to, and you can write WRT for with respect to x. That's how you say dy dx. All right, this thing, the way that you say this is y prime. And y'all, the little like asterisk, this little guy, that is pronounced prime in calculus. We say prime if we have a little, or apostrophe, sorry, not asterisk. The apostrophe means prime. We say y prime, and that just means the derivative of y. We don't know what variable it's with respect to, but we know that means to take the derivative of y. All right, and then this last one is dx. So you can read the dx of f of x. And that means the derivative of f of x with respect to x. All right, really quick, the with respect to comes from the denominator. So do you see how we have dx in the denominator? The with respect to is the d, and then x is in the denominator. So with respect to x, that's because we have dx in the denominator. Okay, now let's find some derivatives. We're going to use both definitions of the derivative, both limit definitions, to find the derivative. So the first limit definition of the derivative, I'm going to zoom out. Actually, no, I'll leave it like this. Okay, the first one, I did it. Oh, I'm going to try to keep my colors consistent. Sorry, y'all. I did that in blue, and the second one I did in green. Cool. So the first one was limit as h approaches 0 of f of x plus h minus f of x over h, right? So the first thing I'm going to do, we have a function. We have the function, find the derivative of f of x at x equals 5. Cool? That's what we're trying to find. So the first thing I like to do is break down these two pieces. So f of x plus h, and then f of x. So f of x plus h, f of x plus h means take x plus h and plug it in where you see an x. So we're going to this function, and we're plugging in x plus h everywhere we see an x. So we see x plus h squared plus 2. Let's simplify it because we're going to need to. Equals, I don't know if y'all know the trick, but that will be the first term squared, x squared, plus 2 times the first term x times the second term h, plus the last term squared, h squared. That will always work that way when you have a quantity squared and two pieces in the quantity. Okay, plus 2. Sweet. That is f of x plus h, so that's the yellow piece. So f of x plus h is this thing. All right, now, oh shoot, y'all, hold on. Let's plug in x. Yeah, let's plug in x. Sorry, x equals 5. So at x equals 5, we need to find f prime of 5. So, oh gosh, hold on. This is the derivative at x equals 5. So f prime, oh yeah. Let's just write it down. F prime of 5 equals, don't worry, I got y'all. Hold up. F prime of 5 equals, okay, the limit as h approaches 0, and then we'll plug in 5 for x. So f of 5 plus h minus f of 5 over, okay, h. There we go. So now let's actually find that yellow, hold on, x plus h, that yellow and green. I was just writing the definition that we used, and then I forgot to plug in x equals 5. So now let's find f of 5 plus h. So we get f of 5 plus h equals, there we go. And then we plug in 5 plus h anywhere we see an x. So we get 5, our function is x squared plus 2, right? So we get 5 plus h squared plus 2. And now we use that trick. First quantity squared, 25, plus 5 times 2, 2 times 5 times h, plus h squared plus 2, so equals 25 plus 10h plus h squared plus 2. That's the yellow stuff. Cool. F of 5 plus h is equal to this. Now let's find f of 5 really quick. That should be very fast. So that means plug in 5 for x in our function. So that's 5 squared. F of 5 equals 5 squared plus 2, which equals 25 plus 2 is 27. Let's leave it like this though, and I'll show you why in a second. F of 5 is 5 squared plus 2. Okay, now we can plug those things in. So let's go ahead and plug those into our limit. So f prime of 5 equals the limit as h approaches 0 of the yellow is 25 plus 10h plus h squared plus 2. And then we have minus 25, because 5 squared is 25, plus 2. You could say that equals 25 plus 2, but I don't want to simplify it all the way yet. You'll see why. Over h. All right, sweet. This is why I didn't want to simplify all the way. Things should cancel when you do this. So we have 25 minus 25. So those 25s cancel out. Then we get 2 minus 2. Those 2's cancel out. So let's write what's left. Equals limit, don't drop your limit as h approaches 0 of 10h plus h squared over h. You can factor out an h, so equals limit as h approaches 0 of h 10 plus h over h. Cross those out, and we're almost done. F prime of 5 equals limit as h approaches 0 of 10 plus h, which equals, solved by substitution, 10 plus 0, because it's a limit, equals 10. Okay, we found the derivative to be 10 using the first definition of the derivative. Sweet. Let's find the derivative using the other definition. We should get the same thing. All right, again, this definition that we just used, the first one, is the most common. So you should know how to use it. It's important to know. All right, let's do the next one. So now we're going to use, I'm just going to write the basic definition. We need the limit as x approaches a of f of x minus f of a over x minus a. And we're going to say a equals 5. At a equals 5. So this time, whatever you're trying to like find the limit at, or the derivative at, whatever x value, that's what you're plugging in for a. So let's go ahead and now say, okay, f prime of 5 equals the limit as x approaches a equals 5, right? So 5 of leave f of x the same minus f of 5 over x minus 5. Sweet. And we're going to do the same thing. We're going to find, let's see, f of x is just your function. So f of x is just your function. And we already found f of 5 in the other example in green, right? Sorry, those greens are kind of conflicting. But f of x, f of x equals my function, which is x squared plus 2. And then f of 5, we already found to be 25 plus 2, right? Yeah, 25 plus 2. And remember, we're not going to simplify it yet. So now we just need to plug in for the blue and the green. So let's go ahead and do that. Make sure you do not drop your limit. So we say f prime of 5 equals the limit as x approaches 5 of f of x was x squared plus 2 minus f of 5 was 25 plus 2 over x minus 5. Remember, there was a reason we did not add the 25 and 2. Usually things should cancel, so we have positive 2 minus positive 2, which cancel out. And now let's go ahead and simplify and solve our limit. So equals limit as x approaches 5 of x squared minus 25 over x minus 5. If I plugged in 5 right now, if I substituted right now, I would have a problem. I would be dividing by 0. So the good news is we can factor the top. So we get f prime of 5 equals the limit. Actually, let me just factor over here. Limit as x approaches 5. This is x plus and minus 5 because of difference of squares. X minus 5. Sweet. So now we're going to take the limit as x approaches 5 of just x plus 5 is left, and we can substitute now. So 5 plus 5 is 10. That is the derivative. Well, guess what? We got the same thing. Same thing. No matter what definition you use, whatever limit definition you use, you should get the same thing for the derivative at a specific x value. Okay, now let's very quickly talk about tangent lines, and then y'all are done with notes. So let's find the line tangent to the curve. This is the curve from the previous example that we used. So let's find the line tangent to this equation that we used before at the point 5, x equals 5, and then y equals 27. All right, cool. Before we find the line tangent, we need to know the point slope equation of a line. So let's do that. Point slope, oh shoot, sorry y'all. Point slope equation of a line. And I'm sure y'all know this. Y minus y1 equals m times x minus x1. And then you have two things that go into this equation. You have the point that goes into this equation, which is x1 comma y1. And you have the slope. This is going to be super important for calculus. Okay, so really quick, our point is x1, y1, but what's the same as slope in calculus? Slope of the tangent line in calculus is the what? Tell me, what is the slope of the tangent line in calculus the same as? All right, the slope of the tangent line in calculus is the same as derivative, so m is going to equal f prime of x. All right, so this is how we're going to write the tangent line equation using this equation of a line. So that's the equation, and then we need the point and the slope to do so. So now let's actually do this problem really quick. Find the line tangent to this graph at the point 527. All right, anytime we're finding lines tangent, I want y'all to write down the two things that you need. That's what I want you to start with. So in our notes, we're going to write point. We're going to write slope and see what we know. Do we know the point? Yes, they gave us the point. 5, 27. Do we know the slope? Well, time out. This is the equation we just used, f prime of x. Do we know f prime of 5? Yeah, we just found that over here. We just found that previously in our notes. F prime of 5 was equal to 10. So good news, we don't have to do that again. So we're just going to say f prime of 5 equals 10. And now it's as easy as plugging that into your equation. So equation of, let's say equation of tangent line at x equals 5. Here we go. Y minus y1 is 27. This is x1, y1. Equals, slope was 10. This is m. X minus x1 was 5. All right, and then usually for FRQs, you can leave it like this, free response question. That's what FRQ stands for. For short answer, or sorry, for multiple choice, you have to actually solve. So let's practice that. We are going to say y equals, we're adding 27, and we're going to distribute the 10. So we have 10x minus 50 plus 27, and then you would simplify from there to get your multiple choice answer. Okay. That was a lot of notes. Good work. Hopefully you got it all down, and we will practice now.